Okay, so for part 2 now. We're going to look at a scenario here where Thomas is looking to create a garden that has an area of 36 square feet. He would like the length of the garden to be 5 feet longer than the width. Find the length and the width of the garden. So this is obviously going to allow for Thomas to have some variable widths and lengths here, potentially. That's what type of formula we're looking at, but we want to constrict things to an area of 36 square feet. So I'm going to write down a couple things first. I'm going to write down that my area is equal to 36 square feet. I also know that my area is equal to my length multiplied by my width. Now to get a better idea of this, I'm actually going to draw a garden here. Since we know my width and length are different sizes, or lengths I should say, we can know that there's going to be some sort of rectangular shape. So one side would be my length, one side would be my width. I'm told that the length of the garden is to be 5 feet longer than the width. So I can redraw this object now. I'm going to draw it again. And then my length is equal to the width plus 5. It is 5 feet longer than the width. We've noticed that if my width is W, W plus 5 is a larger measurement. Okay? Now, going back to my formula for area, area is equal to length times width. I know that my length here is equal to W plus 5. So I can say then my area is equal to W plus 5, which is my length, times my width. If I look at that, then I know that my area, I can distribute this. So my area is equal to W times W plus 5. My exponents on the W are 1. So I'm going to have W as my base. 1 plus 1 on the exponents gives me 2. And then I have 5 times W for 5W. So my area then, or a formula of my area, or I could say my area as a function of the width is equal to W squared plus 5W. We want to find a case where the area, or A of W, is equal to 36. So we want to find out what W is that our area would be equal to 36. So what we're going to do then is we're going to use our calculator to calculate this. So what I go ahead is I put in my calculator my formula, W squared plus 5W, or in this case I'm using X in place here, doesn't matter. I know that's my input, that's my function. I know that my area, I'm looking for my area is equal to 36 square feet, or my output, or in this case, what we call Y1 on my calculator. So again, I'm going to go in here, and now that I've entered in my formula, I'm going to go to second, graph, and that's going to bring up my table. I am looking for an output of 36, so I scroll down here and I see that at a width of 4, my area is 36 square feet. So again here, I see that with a width of 4, my area is 36. So I know that W now is equal to 4. That's my width. But my length, I still have to solve for my length. My length is equal to my width, we'll use the right color here, plus 5. I know my width is 4, so my length is equal to 4 plus 5. Thus, my length is equal to 9. So I have a length of 9, and that would be 9 feet, by the way, and a width of 4 feet as well. By the way, if you take 9 times 4, and going ahead and doing that, 9 times 4 is 36, so I still have an area of 36 square feet. So we see here, and the nice thing about a formula like this is now, if I can choose how I can grow my area based on a width, I can then find out how to optimize my area from this case as well, because I've now written my area as a function of my width, and the width is such set that my length is always going to be 5 feet longer than it. So this is an area where I might be able to rationally use an expression like this. Okay. Let's go on to our final example. Cameron is also creating a garden. He designs a rectangular garden with a length of x plus 6 feet and a width of x plus 2 feet. We're going to write a function that models the area of the garden. Again, our area is just equal to length times width. In this case, our length, I should say, is 6x plus 6 feet. So now I can say that my area is x plus 6 for my length. And my width, I see, is x plus 2. So therefore, my area is equal to the product of x plus 6 times x plus 2. I'm going to go ahead and create a Punnett square for this. X and plus 6, x and plus 2. I'm going to remind myself that the exponents on x are both 1, so that when I come up with my first square here, my base is x, and then I add the two exponents. 1 plus 1 gives me 2. In my second square here, I'm going to get 6x. 6 times x would give me 6x. In the other square that I'm going to look at, my next square, I'm going to have 2 times x, which is going to give me 2x. And then final square that I'm going to fill in, 2 times 6 will give me 12. I notice I have like terms of 6x and 2x, so I can combine those. Those are going to be 8x. So ultimately, my area as a function of x is going to be equal to x squared plus 8x plus 12. So I've come up with a function that models the area of the garden that Cameron is looking to build. And again, it's a of x is equal to x squared plus 8x plus 12. When x is equal to 4, we're asked to find the area of the garden. So we're going to have a of 4 and that's going to be equal to the quantity of 4 squared plus 8 times the quantity of 4 plus 12. The easiest thing to do would be to plug this into my calculator at this point. I'm going to go ahead and do that. And I'm going to get 4 squared plus 8 times 4 plus 12. As a rule, I like to substitute things in. When I substitute it in, I like to put it in parentheses. I hit enter, and I find out that my area with x equals 4 feet, my area is going to be 60 feet squared. So a of 4 here, or when we're looking for the value of x equals 4, my area is going to be 60 feet squared. And again, I can come up with the area of Cameron's garden based on any dimension of x. We have one final problem here. A square swimming pool is surrounded by a cement walkway with the uniform width. The swimming pool has sides of x minus 2 feet long. The length of the entire square, which includes the pool and the walkway, is x plus 1 feet. So we're asked to write a function for the area of the walkway and then find the area of the walkway when x is equal to 6 feet. So let's start by drawing a picture. The best thing we can do in these situations is draw a picture of what we have. We don't have to be a great artist, but we can draw a square swimming pool. Beautiful. We know that the swimming pool is surrounded by a cement walkway with a uniform width. We'll draw on that in a moment. The swimming pool has sides of x minus 2 feet long, and since it's a square, all the sides are the same. Now the length of the entire square, which would include the swimming pool plus the walkway around it, so I'm going to draw the walkway around it now, okay? Including the pool and the walkway is x plus 1 feet. And we're to assume that a square swimming pool is surrounded by a cement walkway with uniform width. That means this is also x plus 1. Okay? So we're to write a function for the area of the walkway. Well, the area of the walkway is the entire area minus the pool. So it's all the area I've shaded in green minus the area in blue. So let's find our two items. We first have the area, the total area. So we have to find the total area. The total area is just going to be the x plus 1 quantity squared. That's the total area we have here. Make that colored for ease of recognition here. The area, now the total area is not what we're looking for the area. We want to find the area of the walkway. Well, we also have to know the area of the pool. The area of the pool is just the quantity of x minus 2 squared. The area now of the walkway is just the total area minus the area of the pool. That's the area of the walkway. So, the area, total area, our total area is just x plus 1 quantity squared. Drawing in our Punnett square, we'll put the exponent of 1 on both x's. X times x will give us x squared from adding the exponents of 1 and 1 to give us 2. X times 1 is 1x. 1 times x is also 1x, and 1 times 1 is 1. When we look at that, we're going to get x squared plus 2x plus 1. That is the area, the total area of our pool and walkway. Of course, we're just looking for the area of the walkway. Our area of the pool would be given by x minus 2 quantity squared. X with an exponent of 1 on it, minus 2. X with the exponent of 1, and minus 2. Again, we're going to have x squared minus 2x minus 2x plus 4. So the area of the pool is now equal to x squared minus 4x plus 4. In order to continue this, the area of the walkway then is just the quantity of x squared plus 2x plus 1 minus, that's the area of the total area, minus the area of the pool, which is x squared minus 4x plus 4. In order to do this problem, this is a subtraction of polynomials. We're going to take our negative sign out front here and distribute it to each term in that second polynomial. What we'll end up with is x squared plus 2x plus 1 minus x squared plus 4x. We flip the signs again. That is our goal here. Minus 4. Going ahead and identifying my like terms here and combining them, I see my x squareds will cancel out. My 2x plus 4x will give me 6x minus 6x, and 1 and negative 3, or negative 4 added together will give me 6x minus 3. That is now the area of the walkway. I'm now asked to find the area of the walkway when x equals 6 feet. As we see here, we're going to substitute 6 in for x. So the area of the walkway when x equals 6 feet is 6 times 6 minus 3, which means the area of the walkway when x equals 6 feet is 33 square feet. All right, that completes that final example. Go ahead and get started on your 7.8 worksheet. If you have any questions, we will be back tomorrow and should be able to go over that. And we'll start the review process. Our test for this unit will be on Tuesday.